Hi all, today we'll discuss some more information about the cache. All of you know that cache memory is really a fastest memory and it follows the principle of locality of reference. So the locality of reference is of two types. One can be temporal locality of reference, another one is spatial locality of reference. So the temporal locality of reference is that when a memory reference has been done for a particular memory location by the processor, the same memory location can be accessed in near future. So better keep that particular word in cache rather than main memory. This is a temporal locality of reference. When it comes to spatial locality of reference, the spatial locality of reference says that when you refer a particular word in the memory and its nearby memory words may be accessed in future, so place those nearby memory locations in cache memory. This is called spatial memory location. So the cache follows the principle of locality of reference, and locality of reference is of two types. One is temporal locality of reference. Temporal locality of reference is that when you access a particular word in the main memory, let's assume this is a memory, this is main memory, and you are accessing a particular word by the processor, then it is an estimation that this same memory word would be accessed in near future. So transfer this to the cache memory. This is called temporal locality of reference, and the spatial locality of reference. The spatial locality of reference says that when you access a particular word in the memory, when processor issues an address 2035 or some virtual address which is converted into 2035, and this memory word would be presently the processor accessing, and it is an estimation that its nearby memory words 2032 or 2033, 34, 36, those can be accessed in the near future. So better place those words in the cache memory. This is called spatial locality of reference. And the best example for spatial locality of reference is array. Because in array, the elements are homogeneous elements, and the speciality of the array is that the elements has to be stored in a contiguous memory location. Contiguous memory location in the sense they have to be stored in consecutive memory locations. Example for consecutive memory locations are like, if a particular the first element of an array, let's assume this is my integer array 5. Let's take a simple array of 3 elements. So this is the declaring of an array in C language. So you are initializing an array, you are creating an array A of size 3. So this is called A of 0, this is called A of 1, and this is called A of 2. So these three elements in the memory are stored at consecutive memory location. If this is my physical memory, A of 0, 20, 25, 30. So this is A of 0, this is A of 1, and this is A of 2. Storing at, let's assume 35, 36, 37. See, this is the address, this is value. This value refers to this array element. User have to access by this way. If the user says A of 0, let's assume the statement is like print A of 0. Then the address, the base address A contains 2035. So this 2035 is referred. So when a processor issues address 2035, then uh, the spatial, if the cache memory is a technique which follows the spatial locality of reference, then it is a clear guess that in near future the programmer may access or the processor might issue an address 2036 and 2037, because already you accessed the programmer accessed 2035, so there are more chances that the processor might issue an address 2036 and 37. So place these 2030, 25 and 30 with 2036, 37 addresses into cache memory. So this is called spatial locality of reference. And the first one, temporal locality of reference. The temporal locality of reference, the best example is for loop. For temporal locality of reference, the best example is for loop. Let's assume I take a simple example of printing I value for 10 times. 0 to 9 is printed. This is a simple for loop. And here the body of the for loop contains a single statement, that is printf. But the point is that this statement has to be executed for 10 times. So this body of the loop has to be iterated for 10 times. So what we do, you know that when the processor issues an address to access the memory for this printf instruction, let's assume this printf instruction is stored in the main memory, particular 1001 address. This is my printf statement. Remember, the main memory contains both instructions and data. So when the processor issues an address 1001 and it knows that it is a for loop, so this has to be executed at least 2 times, or sometimes 10 times, 100 times, 1000 times. So when processor identifies this, that it is a for loop, then the body of the loop, maybe it is containing one statement in this case, but let's imagine if the body of the loop contains some 50 to 100 statements which are to be executed for several iterations. And if for n iteration, and if n is very large, then it is advisable to place the body of for loop in cache memory so that the processor can access them in a fast way, because the cache is near to processor compared to main memory. So by the way, we can reduce the execution time, or we can increase the execution speed of the memory. So remember, whenever you say cache, just get uh, just recollect the concept that cache follows the technique of locality of reference. Moreover, locality of reference is of two types: temporal locality of reference and spatial locality of reference. Now we discuss some advanced concepts of cache which are very important. In cache design, what happens? Let's take a simple example before understanding the need for discussing cache design. If the memory contains 2 power n addressable words, what does it mean by? Let's take a main memory. The main memory, what is trying to say? The capacity of the main memory. If this is my main memory and this has been divided into, let's assume 0, 1, 2, 3, 4, 5, 6, 7 for simple case. So this main memory is divided into memory locations, or these memory locations are also called memory words. How many memory words are there? 0 to 7. So total 8 memory words. So how I should say, if the memory contains 8 memory addresses, but 8 can be written as 2 power 3. So I can slightly change the sentence such as the main memory contains 2 power 3 addressable memory words. I hope you are getting. So how I framed a sentence? The main memory contains 2 power 3 addressable memory words. Why I am converting this 2 power 3, the 8 into 2 power 3 means 3 bits are required or sufficient to locate 8 memory words. 3 bits are sufficient. How? I'll explain. See, 3 bits, let's assume these are the 3 bits. In 3 bits I can store 0, 0, 0. I can store 0, 0, 1. I can store 0, 1, 0. I can store 0, 1, 1. So this is nothing but 0. This is 1. This is 2. This is 3. Similarly, I can stay 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. This is 4. This is 5. This is 6. This is 7. So using 3 bits, I can identify 8 memory words. See, this is address of first memory word. Let me explain. If this is my main memory, 2, 3, 4, 5, 6, 7, 0, 0, 0 is the address. This is address. Let's assume this is address. This is main memory. 000 means first address. 001 means second address. 010 means third address. 011 means fourth address, since we are starting from 0. Next 100, 101, 110, 111. So if I divide the main memory into 8 words, it's enough to have 3 bits for 8 different locations, 8 words. It's enough to divide, it's enough to have 3 bits. So to identify 8 words in the memory, 3 bits are enough. What is the relation between 3 and 8 means? 8 can be written as 2 power 3. This is the basic, and it is very important to understand this concept. Next, so now you understand this statement, that is, if the memory contains 2 power n addressable words in main memory. Now how can you interpret this? So that means the main memory has been divided into 0 to 2 power n minus 1 different words. Why minus 1 is required? See, in the previous example I said, if the memory is divided into 8 different memory locations, 0 to 7. 7 can be written as 8 minus 1. 8 means 2 power 3 minus 1. Similarly, just replace 3 with n. Instead of 2 power 3 minus 1, you are getting 2 power n minus 1. So when someone says the memory is divided into 2 power n words, then you should assume this figure. So 0 to 2 power n minus 1 words. The memory, main memory or physical memory or RAM, has been divided into 2 power n words, starting from what would be their address. So the address for these 2 power n words means the first address would be 0000. How many zeros? N bits. Last address would be 11111. How many? N bits. This is the address, starting address and ending address. This refers to 0, this refers to 2 power n minus 1. So you should understand that the memory contains 2 power n addressable words. That means divide the main memory to 0 to 2 power n minus 1 addresses. These are the addresses. Now the memory can be broken up into blocks. Now you are dividing this memory words, you are grouping the memory words, and you are calling them as block. See, when we discussed about virtual memory technique, I hope you remember that we divide the main memory into pages. And here I am saying that the main memory is divided into some blocks. So dividing the memory into pages is for managing or implementing a technique called virtual memory. But dividing the main memory into blocks is for faster execution and is to manage the cache memory. So the memory can be broken up into blocks with k words per block. This is important. I said you group some memory words and call it a block. How many memory words? K memory words. So if the memory contains 2 power n addressable words, and memory can be broken up into blocks with k words per block. Now can you guess how many number of blocks would be there in the memory? So first there are 0 to 2 power n minus 1 addresses. So total 2 power n words. I said group k words and call it as one block. So how many blocks? Simple, 2 power n divided by k number of blocks. It's a simple logic. Let's take a simple example. It's really important to understand this concept, how cache is designed. Let's assume I divided 2 power n minus 1. So there are n as 32. So 2 power 32 words are present in the addressable words are present in the main memory. And let's assume I divide like 32 words into one block. So k is 32, n is 32. So how many blocks would be there means total number of words are 2 power 32. Divide group 32 words to one block. So by 32. 2 power 32 by 32. How much it will be? 2 power 32 by 32. 2 power 32 by 32 means I can write 2 power 5. So 2 power 32 minus 5, that is 2 power 27 blocks. I think it is very big. In general, it's not the case. It's like the k would be some 2 power 20 blocks, let's assume. K word contain 2 power 20 words. N is equals to 32. So 2 power n by k. 2 power n means 2 power 32, 2 power 20. So 2 power 12 blocks. So like that. I hope you are getting. So the memory can be broken up into blocks with k words per block. So the total number of blocks would be 2 power n divided by k. Now the cache, how the cache is designed. Cache consists of C lines or slots, each consisting of k words. So cache consists of C lines. Line means or slot, each consisting of k words. So divide the cache consisting of 0 to C minus 1 blocks. Simply you say this is a block, but you are just calling as line or slot. 3 blocks. Let's assume I have 3 blocks. So this is my cache. First, this is my main memory divided into block 0 to block 2 power n divided by k minus 1. You should understand this. It's very important to understand why 2 power n divided by k. I hope you understand 2 power n divided by k. So 2 power n divided by k means 2 power n means total number of addressable words in the memory, and I grouped kk words, so I get some k blocks. How many blocks? 2 power n divided by k number of blocks I got. So if you give the numbers to the block, total number of blocks are 2 power n divided by k. But you are giving the first block as a 0 block, 1 block, like that. 2 power n divided by k minus 1 block. Let me draw the picture because it's really important to understand this. This is my mind memory. Let's assume it is 2 power 0 to 2 power n. Yes, minus 1 words are present in the main memory. So the main memory contains 2 power 0 to 2 power n minus 1 word. So total 2 power n words. I am grouping kk words as one block. This is block 0. Next again, next k words, block 1. Next block 2. Like that, how many blocks? How many blocks means total words are 2 power n. By dividing them by k, grouping. So 2 power n k blocks will be there. But what about their address? Number. If I give number to the block, first is 0 block. Since I am starting from 0, the last block address would be 2 power n k minus 1 block. Simple. I hope you should understand this. Yeah, you are getting the point. So I have a main memory. This is block 0. This is block 1. Block 0 contains some k words. I'm grouping the words. The main memory contains words, not blocks, but I'm grouping the words into blocks. So the first block, second block. Now I'm talking in terms of blocks, not in terms of words. What's the last block would be? Since there are total 2 power n divided by k blocks, the last block address would be 2 power n k minus 1. Since I'm starting from 0, if I start from 1, block 1, the last address would be 2 power n divided by k. But I'm starting from 0, and the reason why I'm starting from 0 is that just to make use of the address 000. 000 is also an address. You should use it. For that I am starting from log 0. So the cache consists of C lines or slots, each consisting of k words. Now in this case, this is my main memory. In this case, I have a cache memory, and this cache memory is also divided into blocks. How many blocks? C blocks. What would be their address? 0 block to C minus 1 block, right? So that's what explaining here. The picture, this is the cache memory. Is calling line in cache, block in memory. Both contains the same number of words, that is k words. Line 0 to line C minus 1 because we have C slots. How to map blocks of memory to lines in the cache? It's very important to understand because you may transfer the block 0 as line 0 and block 23 as line 1 and 54 as line 2. So how to track which blocks are present in cache? So the goal is cache design. The purpose of cache design is which blocks are present in cache. So this is the goal of cache design. It's really important to understand this concept. For that, there are various factors that you should remember, that you should know. Let me explain in detail because it's very important to understand the design of cache. First one, size. What size says? Of course, there are various factors like size. First, we will take one by one. Size. Cache size. What is mean by cache size? Any guess? Cache, you are saying cache is divided into C slots or C lines. What is a slot? Slot contains K words. Now, what is mean by size means it can be K. That means how many words should be grouped to form a block. If someone asks you design a cache memory, then you should run some algorithms which will give you the optimal value of k. Optimal means what is the correct value of k. What is the correct value of k? Second one, okay, you decided that k to be, let's assume 32. That means you are dividing the k. So that means by cache size. The cache size means, now I hope you are understanding what should be the value of k and what should be the value of c. C means how many blocks your cache memory should be divided into. I think you decide k based on size of cache, you will come to, you can calculate c indirectly, but so everything depends upon k. So the cache size means, in my opinion, what should be the size value of k. So the size matters. How it matters? More cache is expensive. So size means, what is trying to say, what should be the c value? Yes, our guess was correct. What should be the c value? What should be k value? So whether c can be large, medium, or small. If it is small, it is like registers. If it is large, it is like main memory. So it should be medium. But what is that medium? See, if the size of the cache is large, then it takes more time to access particular word. Yeah, here you should understand this point. See, if I have a big box, then searching an item in that big box takes much time. If I have small box, searching an item in that small box comparatively takes less time, more time for searching. So the cache cannot be uh, large volume, large capacity. Another reason is that it is very expensive. Cache is very expensive. You can't keep its size very big because it is very expensive. It becomes very costly. So the size depends upon what is the factor. C should not be very large because it cost would be high. If not, then it should not be very small also, because it's, for small we have registers. So its small should be medium. What is that medium? How to find out it? Next, speed. Cache is very fast. Up to a point, diminishing returns as a cache increases size. I tell you, it is a speed, but if you increase the size, its speed would get reduced. And if you increase the size, it also takes longer time to search a particular word. So this is about size. So it's really important to keep what is the value of C, what is the value of K. Next important thing is mapping function. See, mapping means main memory, how to identify which block is present in cache. It may contain block 20, block 35, block 40, block number 20, 35 and 40. So these three blocks are present in the cache memory. But the address comes from processor, remember? The address comes from the processor, and first processor verifies whether particular word is available in the cache before searching in main memory. It will verify in cache, and it tries to see whether the particular word is present in the cache rather than main memory, because it would be very in less time you can get a memory word if it is in the cache, and you know this is called cache hit. If the word is not available in cache, it is called miss. So suppose we have the following configuration. First you should understand this configuration thoroughly. Word size is of 1 byte. Yeah, we got one more point. So this is my main memory. Main memory is divided into 0 to 2 power n minus 1 addresses. It contains total 2 power n words. First address is 000. First word address. The last word address is 2 power n minus 1. And this is the place we are simply keeping a blank. Now what is saying? Word size is 1 byte. 1 byte means 8 bits. So the word size is 1 byte. So how many such bytes are number of bytes are there in the main memory? 2 power n bytes. So if somebody says my main memory size is 2 power n bytes, means you have to translate into 2 power n into 1 byte. So 1 byte is the number of bits where you can store a word, data or instruction, and there are such 2 power n words, and each word can store 8 bits. Now cache size is, the word size is 1 byte. Cache is of 16 bytes. Now you should understand. Cache size is 16 bytes. 16 can be written as 2 power 4 bytes. Now 2 power 4 can be written as 2 power 4 into 1 byte. 2 power 4 into 1 byte. So 1 byte is the one capacity of one word. 2 power 4, yes, such how many such words are present means 2 power 4, that is 16. So if I draw the cache, this is cache size. Its capacity are 0 to 7 bits, 0 to 15, able to understand? It can store 16 words, and each word can store 8 bits. Now cache line or block size is 2 bytes. That means k is equals to 2. You are grouping two words of size 1 byte into one block. So tell me how many blocks cache contain. Let's assume this is my cache. It contains 0 to 15 words, and you are saying two words are one block. The block size is 2 because k is equals to 2. See what you're saying, block size is 2 bytes. Block size is 2 bytes. 2 bytes means 2 into 1 byte. 1 byte is equals to 1, so 2 words. So I should divide the cache total 16 words, and 2 words I am calling it as words, so there will be 8 slots. That's what he's trying to say. We are going in detail how cache would be because it's important to understand. Simply going through the concepts doesn't make you an expert. Now you know what is meant by a memory word, how many words a main memory can contain, what is the size of the cache, all these things. It's really important to understand. Next, I have, so the cache contains 8. What is the value of k? 2 bytes. Block size. Cache size is 2 bytes. Cache size is 16 bytes. How many blocks it contains? 8 blocks. Now we need 8 addresses for a block in the cache. Yes, we need, because since we have 8 blocks, we need to address those 8 blocks starting from 0 to 7. How many bits are required? 3 bits. 3 bits are required to address 8 different blocks. Let's assume main memory capacity is 64 bytes. So the capacity of the main memory is 64 bytes. What does it mean by 64 bytes? 64 into 1 byte. Why I am each time referring as a 1 byte? Because the word size is 1 byte. 64 I can written as 2 power 6. So there are 2 power 6 words. The size of the word is 1 byte. 2 power 6 words starting from 0 to 2 power 6 minus 1, that is 63. 0 to 63. Now you know that the block size is 2. So when I say the block size is 2, divide 64 by 2. So you get 32 blocks, 0 to 31, and 5 bytes are required. So the main memory is of 64 bytes. To address this we need 6 bits. Relay reference to 64 bytes and 32 memory blocks. Somehow we have to map 32 memory blocks to 8 lines in the cache. The processor issues an address of 32 memory blocks. And the goal is to we have to map these 32 memory blocks to 8 blocks, because out of these 32 blocks, if the main memory contains, simply saying main memory contains 64 words, so 32 blocks. The cache contains only 8 blocks, so we should map this 32 blocks to 8 blocks. Somehow we have to map 32 memory blocks to 8 lines in the cache. So multiple memory blocks will have to map to the same line in the cache. The hint is that multiple memory blocks will have to map the same memory cache. That is the goal. You will see that.